welcome to episode 12 of Writing a 6502 Assembler in Assembly Language. Last time, the scanner basically seems to work, but there are a few small things that need to be done. First off, we have to handle comments because we were getting an error for comments. And second off, there's all sorts of important words in our assembly language which are not just regular names like a symbol or something like that, but instead they're important, like the opcodes themselves and the pseudo-ops and things like that, so we have to take care of those. So let's first go in and take care of the comments. That should be very easy. We're just going to look at the scanner, the top level of the scanner here. This is our code to print out the tokens. That's a debug code. Here we go. Okay, so here's the scanner. And right after we check for white space and new lines and stuff like that, right? Okay, what it's doing here is it says if it's not a white space character, we're going to go to scan 3, which is right down here, and we check for names. Actually, what we need to do here is not check for names yet. We need to check for comments. Okay? And let me, because we're adding in, it's a new label, I'm just going, I think we have scan 12, scan 13, okay. So I'll just call it scan 15. Why not? Okay. Check for comments. Scan 15. All right, so comments will begin with a semicolon. And if we don't have a semicolon, we will just go to scan 3. And then, of course, here, this has to go to scan 15, which is kind of first thing, look for comments. Okay, so if we get a comment, all we're going to do is just throw away characters until we get a new line character turn into file. That's it. So we'll JSR get C to get a character. And if it is a end of file or something like that, well, first off, we'll check for end of file by comparing y to 0. If it's not 0, that is, it's end of file, let's go to 15a. All right, if it is now not end of file, we're going to compare to new line or line feed character. If it's not a line feed character, we'll go back to, actually, this should be maybe 15b. And here is 15a. All right, so if it's not a new line, we'll go back to scan 15a and just get another character. So get a character, check and see if it's a new line, end of file. If it is, go down here somewhere. This will be the place where the comment's finished. Okay. Then otherwise, see if it's a line feed. If not, go to 15a. That means get another character. And also check against 13 since we're dealing with carriage returns here. If it's a carriage return, if it's not a carriage return, go to 15a. Whoops. There we go. All right, and if it is not an end of file and not a, that is to say, if it is an end of file, okay, then we get on here. If it's not a new line, if it's not a new line, we go up here. I'm sorry, that's not right. If it's a new line, we need to go ahead and go to 15b. Okay, so is it end of file? If yes, 15b. Is it a line feed? So it's not an end of file. Is it a line feed? Yes, 15b. Is it a character return? No. then go up to 15A. So the possibilities that get us down here are end of file, line feed, and not carriage return. All right, so here's 15B. And all we're going to do here is just unget the character. All right, so we unget this end of file, line feed, or carriage return. And then we jump right back up here to the beginning here. Well, where this is just the top loop of the scanner. And of course, since we just ungot an end of file, line feed, or carriage return, it will in fact, when it goes up there to scan 0, it will get this end of file, line feed, or carriage return and handle it appropriately. So the way we check for comments is if we see a semicolon, we just basically eat up all the characters until we get end of file, line feed, or carriage return. If we get any of those three, we unget it and go back to the top of the scanner. So that means if I have a comment if I have something in my source file, now in this assembler we have a star for a comment in the first column, but assuming that it was for my assembler, we'd have something like this, like okay, comment, and this would look to the scanner just like an end of file. I mean, just like a line feed, like a end of line, right? Because it'll see this, throw all this stuff away, and then it'll go back up to the top and get this end of line. Okay. Good. So that should take care of that. And what we should see here is that if I have a test. Remember, let's just look at the catalog. I have that file called test. Okay, test, and I'll send that to the printer so we can see. Yeah, now we don't get those errors in here that we got from the comments before. Okay, so we've taken care of that. Now, let me show you. Here is the documentation for the assembler. And here we have the area on the section on directives. We have possibilities .byte, .addr, .if, .else, .indef, .extern, .text, .data, .bss, .abs, .65CO2, .65CO2. Oh, I see. Sorry, that was supposed to be .6502, .65CO2. And then we have our opcode starting here. So what we need to do is basically we're going to have to, once we get a name, check and see if it's equal to one of these things. And it's probably a bad idea to go through a big list of names and compare each of them, so we'll do it with a binary search. That'll be the fastest way to do it. And the only really thing that we have to worry about with a binary search is we have to make sure that all of our names in the table that we search are in order. All right. Now, actually, what we're going to need for a binary search is a string compare function. So let me go ahead and I'm just thinking, where do I want to put my string compare? Is it... Okay, so our output stuff is here. Input here. You know, it might be a good idea. I think what I'm going to do is I'm going to go ahead and move to a new source file. So I'm going to append AS1 here. And I want to remember these things because I want that at the beginning of, whoops. I want this at the beginning of all of my files. just save that out there, don't delete it. Okay, save, and exit, and new file. Okay, so we have all this stuff again. And now, whatever the name is here of this code segment is also an entry point, so I might as well just go ahead and use it for string compare. And then here I need append AS9. So AS0 appends AS1, which this will be. AS1 appends AS9. And let's go ahead and save that to a new name. Okay, just quick catalog. Yeah, okay. So I'll put other sort of utility functions and things here, I guess. But for now, we'll just do it this way. All right, so I have to think about if I'm going to compare two strings, how do I give the pointers to the string to this routine? I think what I will do if it's just one pointer, I like to pass it in X and Y, but there's two pointers here. That's doesn't really work. So I think what I'll do is I will just something like this. So in other words, you're just going to write the calling routine. The calling routine will just write the addresses directly into this code here, and then call string compare. All right. So we're going to load X with 0. Okay. Load the first one here. Then compare to the second one. Yeah, actually, I want to do it slightly differently. Okay. I'm sorry. I want to set the carry, and here subtract. So I want to actually do the subtraction here. Instead of using, a compare is basically subtraction. What I had there was this, but I want the result in A. Okay, and if the result of that subtraction is not 0, then I'll go to strcomp2. All right, so basically I take a character from the first string, I subtract the character from the second string from it. If that's not equal to 0, then the strings are not equal because they have a different character in that position, right? And so it will simply return the result of this subtraction in A. What that means is if for example, this string here, let's say just in the very first position, this string has an A, this string has a B, then ASCII A minus ASCII B is going to be in decimal numbers 65 minus 66. The result is -1, and it will return -1 in A. What that means is that this string it's going to return a negative number in A, which means this string is less than, in a certain sense, or it comes before alphabetically this string here. This one was A, this one was B, so this one's alphabetically first. Okay, so this is basically just how the C function strcomp works. Okay, if they are equal, then we're going to increment X, and as long as X is not equal to 0, we'll go back up here to get the next character. And if x is equal to 0, that means that these two strings are identical out to 256 bytes, and we will allow that to be considered equal. Well, I mean, we shouldn't have any strings that long anyway. We're writing our code for strings that are less than 256 characters long. If they're longer than 256 characters, then this code is just not going to work very well, but too bad. And we'll just go ahead and move x to a there to make sure I have a 0 in a, because if we're, for whatever reason, comparing strings and they're equal 256 characters long, and they're at least 256 characters long, the first 256 characters are equal, then we'll just call that equal strings. We'll put a 0 and a in return. All right, we still have to now handle the issue of what we come to the end of one of the strings. Okay, so we come to the end of this string. Now, if we get a null here, that is the end of the string is a null byte, and we get a null byte here, then what will happen is that they're equal. So what we should do here, okay, so the two are equal because it's a null byte and a null byte. But we need to check and make sure, right? We actually need to check and make sure that if those bytes we just compared were nulls. If they are, then we're done. Okay. Let's just take this and move it into y. So when we're going to get the character from the first string, move it into y, then subtract the character from the second string from it. So what we'll do here now is we'll compare y to 0. If y is 0, that means the character that we compared here and compared here are nulls, right? And they are not equal. I mean, they are equal. If they were not equal, we would just go down here and be done. They are equal, but what we compared was a null. All right, so if this is in fact a null here, then we want to just go to strcom2. All right, so let's go over it. We're starting x to be 0. That is our index into these strings. We get a character, the first character from the string. We remember it in y. We subtract the character from the second string. If they're not equal, then we go down here. That is to say, if the result of the subtraction is not 0, then we go down here and return the result of the subtraction. So if this was an A and this was a B, we're going to return -1, which means that this string is alphabetically before this string. If this was a B and this was an A, we're going to return 1 here. And 1 would mean that this string is alphabetically before this string here. If they are equal, then let's just assume that the character we compared was not null. Then it would go down here, increment x, and go out to compare another character. If they are equal, so and the numbers the characters we compared in these two strings was the null, then we'll say, okay, that means we're comparing the character we compared null. Yes, it's a null. So that means we're done because we reached the end of both strings and they're equal. And we'll go here and return the 0, which is an accumulator. And the 0 is an accumulator because this subtraction right here resulted in 0 in the accumulator, because these two were equal. 0 minus 0, 0. Okay, that looks good. So I think that will be fine. All right, we'll save that. And we'll go back to AS0. I'm just moving that strcomp function off to a different source file because that source file will have, I'll put other utility type functions that we need there. Oh, notice, actually, look here. This file is 90% full. That means I'm going to go ahead and just stop this. I'll go back to here where we were, and I'll actually do the code to check here, to check if our names are keywords and whatnot here. Okay. So actually, let me just make this an entry point. Whoops. For now, I'll just call this utils. Although wherever it has a start here, this is an entry point. It may not matter. We may never do that. We never need to call this. So anyway, I'm just not going to worry about that. Just move down here. Okay. So now we need a function or a subroutine that's something like is keyword, right? And this will be given a pointer to the string. No, it doesn't have to be, because when we get a name, remember we're storing the name. The scanner stores names and strings it reads in the buffer that we have at location 200. So we know that when we're checking for a keyword, the name that we've read in from the text, the scanner read in, is at location 200. Okay, so what we need here is basically a table of all of these. We need a table of all of the possible keyword names. That is, we need these things. All right. I'm going to go and add these in, and I'll show you how I'm going to do it with a few, and then I'll go ahead and type in the rest off screen, because that's probably super boring. It's not, maybe all of this is boring, but that is purely typing. There's no logic, there's no code and everything, so I'm not going to require you to sit through that. I'll just do it off screen, but I'll show you what I'm going to do is I'm going to have a list of names here, and I'll put in the first few. So byte, adder, if, else, and if. Okay, so for example, I'll have DC. Here's byte. Okay, so that's the string byte. Adder, and remember these have to be in alphabetical. Well, actually, yeah, they have to be in alphabetical order, but this part right here doesn't have to be in alphabetical order. But I'll go ahead and put it in alphabetical order because it's going to be by far the easiest way to see this stuff. Like it's just for looking at the code, you want to see where things are, and if this is not in alphabetical order, then it will just be ugly. But really, this is not the part that must be in alphabetical order for the binary search. That's going to be the table of pointers. Okay. Yeah, by the way, there's one other thing I just thought of, which is that when we're doing this, we might want to do the comparison in a case insensitive way. In other words, if you want to use the text pseudo-op, it could be this or that also would be fine. We might want to allow that. If we do that, then that would also be fine, but yeah. So we will probably want to do that. Okay, else. indif. All right, so this will be it for now. The rest will be done on off screen. But after I type in all these things here, what I'm going to need is I'm going to need some sort of label for these, okay? So, but it just doesn't have to be anything special. I can just say keyword 00 and keyword 01, keyword 02, keyword 03, keyword 04, keyword 05, keyword 6, like this, okay? And now I'm going to have a table. This is the actual table that I will use for my binary search, like called keywords. And this will have an address. For example, keywords 00. Okay, and yeah, there's two ways to do this. I'm going to want to include something here, like for example, this is called right, token 6502. Now, I'm also going to then for that need something here like token 6502 is equal to whatever it is, 140. It's just some number which is different from all other tokens, right? That's what matters. Or this is it's probably a better idea to do it like this. Don't include that. That's kind of a waste of space. I'll have token key. This basically means all tokens that are keywords will start at 140. I think if I remember correctly, I don't have any tokens that high. They're all in the 130 range. It doesn't matter. It could be 150. Okay, they'll start here. And what I'll do is I'll just say which one is in the list. So the first in the list is going to be .6502. That's for sure. And then the rest are going, like this. So basically, this number here, converted to an actual number, will get added to this keyword token and give us the keyword. So that way, I don't have to like define equates for all of the tokens. That, as far as looking at it, it might be nice, but it probably will fill up the symbol table more than I want to do. So, I mean, the symbol table of this assembler here, the orca assembler. So I'll have like this, right? A key W0, so, right? So this is just a pointer. This is a pointer to this string, right? And I think that I can go ahead and put them in here like this. That's something I'll have to check with the orca documentation. But I'm pretty sure that will work right there. So it'll put all of these pointers in there, one right after the other. And notice I put these in order. They're in alphabetical order. So these also will be in alphabetical order. Anyway, now's the time I'm going to go ahead and stop and do this, enter all this stuff off screen. It's purely a typing thing. And then I will be back in a minute or a few minutes. Oh my. Okay, I'm back after quite a bit of typing junk in. So let me show you what I have done. This is in the file AS0. That's my first file. The first thing I've done is I just changed all of these from decimal numbers to hexadecimal numbers. Otherwise, it's the same numbers. This was 128, 129. That's now hexadecimal 80, hexadecimal 81. Then I added these token types here. 90, hexadecimal 90 is going to be pseudo-ops. That's my PSE. Now the rest of these start with hexadecimal A0, and you'll see why in just a moment, why they don't start with 9-1, they start with A0. And these are the different types of instructions that you can have in a 6502 or 65C02 processor. Let me pull this up here. If you look at the documentation, it actually has these broken out here. It has these instructions here as simple machine instructions. These are the opcodes that have the instructions that have only one opcode. There's only one number corresponding to each of these. These are 6502 only, and I have actually in the code broken that out. You'll see in a second. These are branches. Again, 650 CO2 only, so that will be broken out as a separate thing. And these are basically, it's a lot. I'm in the assembler, I'm going to allow you to use these symbols to get long branches. Okay? And so on. These are TRB and TSB instructions, which are 6502 only. So what I have here is, for example, up here, I have what I'll call a CLC type instruction, which would be all of these except for the push X, push Y, pull X, pull Y. All of these are CLC type instructions, and they go as here a CLC token. These, the push X, push Y, come in as push X tokens. The branch instructions, except for BRA, comes in as a BCC instruction. That's because the first one is BCC. And then there's a separate token type for BRA because that's a 6502 only instruction right there. And then there are these type of instructions for the extended branch. Those are JCC type instructions right there. TRB, TSB are TRB type instructions right there. Compare X and compare Y are CPX instructions there. All right, here now, these are all very similar except for that the decrement increment instructions only allow an accumulator operand on 65C02 instructions. On 6502, they do not allow an accumulator operand. So I've broken them out. So you have shift type instructions, that is ASL type instructions, plus DEC type instructions, DEC and INC type instructions there. All right, and I have load X type instructions. And then again, load Y and bit are both in the same thing here, but bit is different on 65CO2. That is to say, bit is the same as load Y on 65CO2 processors, but not on 6502 processors. So these are all broken out individually here as load X type, load Y type, bit type. STX and STY they work together. So those are STX type instructions. Oh, I'm sorry, they don't work together because they have, STX is here, STY and STZ are here. Again, STZ is a 65CO2 only instruction, so that it's a separate thing. STX, STY, STZ. All right, then we have jump type instruction and JSR type instruction here and here. I will point out that the jump instruction has an extra addressing mode on 65CO2. We can't handle that with a different type of token here, but we can handle that in the code that will process a jump instruction. It'll look for that and complain if you're trying to use a 65CO2 addressing mode without having said that you're using 65CO2 instructions. All right, and then we have STA instruction that has its own type because it has its own set of addressing modes that it can use right there. Then we have all of these arithmetic and logical instructions, ADC and CMP, EOR, and ORA and SBC all take the same addressing modes, and those are called ADC type instructions right here. LDA is almost the same except for it has a separate addressing mode on 65CO2. Like all these others can do this, I believe, or maybe they can't. Anyway, LDA is different on 65CO2 than 6502, so it has to have its own thing. That's that right there. And then the break instruction is special, and so it has its own type there. So basically, all of these token types will be returned to tell you what type of instruction you have, and the type of instruction will determine which addressing modes it can use, and also it distinguishes between 6502 only and 65C02 instructions. Okay, that's what these will do. So now I can quit this and go to AS1. Now you'll see I started typing these things in. Now here's all the rest of the stuff, and it's all in alphabetical order. At least I hope I didn't screw something up, but they're all in alphabetical order. Like I said, it's not super important that they're in alphabetical order here, but they must be in alphabetical order right here. And it makes sense if these have to be in alphabetical order, that these also are in alphabetical order. So this is just a table of pointers to each of these strings here. These are all strings with the characters in with a null byte. And these are pointers to those strings. And they're in alphabetical order because we're going to binary search this table. And when we do that, we'll be able to figure out which, well, either if the thing we're looking for is in the table or not, and if it is in the table, which one it is. And once we get the index of the thing in the table, we can look it up in these two tables here. This is what will be returned as the token, all right? And here's all the instructions. So we'll return one of those things that we just talked about as the token. These things here are the pseudo operations. And you see, instead of putting separate names for each of the pseudo ops, I'm just taking TPSE, which was hexadecimal 90, if you remember, and just saying +0, +1, +2, +3, and so on. So the pseudo ops, I don't have special names for their tokens, but they'll be 90, from 90 right here, all the way up to 9B hexadecimal right here. And then this table is the table which will be returned in the toke_val field, the toke_val variable. And for the pseudo-ops, it's just zeros. But for all the actual instructions, it is an opcode for that instruction. For some instructions, for example, the instructions which are type CLC, those instructions are just here, and I'll real quickly pull that up here. It's these guys here. These guys here. And if you look, and the, whoops, I didn't mean to do that. If you look in, not this one, but here, well, I guess this one is fine too. This, I'll do this one here. Okay, there we got it. So for example, these are CLC type instructions. They have only one possible opcode, right? So that opcode is listed down here. Okay, if you're talking about an instruction like, for example, ADC, right, which is the very first instruction right here, I'm returning one of the possible opcodes, hexadecimal 61. Let's look for that. These arithmetic and logical instructions have lots of different addressing modes they can use. There we go. Here it is. I'm returning 61. It's not so important. I just need to return something. The reason I'm returning 61 is because most of these others can be taken by just adding bits to this 61, right? For example, if I want to change it to immediate, I just add an 08 hexadecimal. I just add that in. If I want to change it to 71, I just add 10 to this, and I get this one here. So I kind of, in the situation where there's more than one possible opcode, what I did was I chose kind of the simplest opcode that I can create all the others by just adding setting some bits. I set some bits in this opcode and I'll get all the others. Okay, and like for example, for most of the arithmetic and logical operations, it'll be setting the same bits to get the same, well, here's 2 right here, right? So if I want to change from this addressing mode to this addressing mode, like, you know, I'm returning 61 here, right there, right? But actually it's this addressing mode instead, not this one. Then I'll just add I'll set this bit here, the first bit in the high nibble, I'll set the bit 10, And that will work for this one, and it will also work for this one too. And it should work for all of them, in fact. All of the instructions of that type, all the instructions that have type TADC. Okay, so what we'll do is when we get a name, we'll look it up in this table here with a binary search. If we find it, if we don't find it, it's just a symbol. If we find it, then we'll set return this is the token and return this is the token value. And then that means we'll be able to easily assemble the different instructions. All right, so now all I have to do is actually write that code to is keyword to actually look stuff up in the table up there, binary search. Let's do that. Okay, here's our string compare. We just have to put our pointers in here and here. And in this case, one of them is going to be the pointer in okay, so the text, when we get a keyword, a name that might be keyword, the text for that name is going to be in location 0200, so 0200. And this has to be +1. So we're taking 0200 and storing it right here. Okay, so the other thing we're going to have to do is we need to kind of choose when we're doing a binary search, we'd like to start in the middle somewhere. We're going to choose the middle of this thing, right? So what we probably need is kind of a pointer to the beginning, or an index of the beginning, and an index for the end, right? We'd like to know how many elements are in this table. I say like to know, we need to know how many elements are in the table. So let's, I'll call this is keyword front, is keyword back, and let's see if I just make this, I'm just trying to think, should these be pointers, or should they be just indexes? Let's make them pointers right now, or addresses. Okay, so I need to make, so what I have to, if these are pointers, if these are addresses, I have to store here the address of the table. So that's going to be keywords. That's the name of the table. Okay, the little byte of keywords stored into is keyword front, and the high byte of the address of this table is keyword front +1. And now I need to store in this address, I need to store here the end of the table. And the end of the table, end of this table is actually the beginning of this table here. So I'm going to store this address, keytoke, is keyword back. +1. All right, so what I'm doing here is I'm making some pointers here, And is keyword F for front is the address of this byte right here. That is the beginning of the table. Is keyword B, is keyword back, is the address of this byte right here. And that's what's important is not that it has anything to do with this table here, but rather it's one byte past this table. So it's the address just past the end of this table. All right. So now in here, what I'm going to have to do, or what I want to do, that is I want to find the average of these two addresses. Okay? The average of these two addresses will be the address of the middle element of the table. Right? Now let me just briefly think, what if the table has an odd number of elements? I mean, right now it doesn't, or yes it does. It does have an odd number of elements, okay? So if it's like, you know, like there's 1, there's 2, there's 3 things in the table. If this were address 0, 0, 1, 2, 3, 4, 5, then the end of it would be at address 6. All right, so we're assuming that this is address 0, and then the next thing here, which is something, it doesn't matter, whatever it is address 6. Then if we said we'd make the average here would be 3, right? 6 plus 0 is 6, divided by 2 is 3. We would do 0, byte 0, byte 1, byte 2, byte 3. Oh, that's no good. We don't want that. We don't want to have this as a pointer to something, because that's pointer. We don't want a pointer to here. That would be terrible. All right, so we definitely don't want that. So what we're going to have to do if we do it this way with these addresses is we're going to have to find the average, right, which in this case would be 6 plus 0, just for our little sample case here, and divided by 2, which would be shift right by 1, all right, and that would give us a 3. But what we're going to do with this 3 is go ahead and basically remove the low byte by, for example, ANDing it with FE. That will clear out the low bit. Sorry, not the low byte, the low bit, and that would make it then a 2, which would put it 0, 1, 2 right here, and that's fine. Okay, so the calculation we have to do is the is keyword back address minus is keyword front address. I'm sorry, yeah. Okay, no. We can do is keyword back address plus is keyword front address divided by 2. But we do have an issue that it's unlikely because of where these things are going to be in memory, but this plus could overflow. So maybe it would be best to do it like this. Is keyword back address minus is keyword front address. In terms of this here, let's just assume this is not 10 and 6. Let's assume it's 24 and 30 or something like that. All right. So in terms of this here, what we're going to be doing is 30 minus 24, all right, which gets us 6, right? That gets us 6. And then what we do is 6 shifted right twice. Okay. What's really 6 shifted right once, which gets us 3, and then 6. We could say 6 and FE to clear the low byte of 6. I'm sorry, 3. We have 3. 3n fe clears the low byte, which is then 2. Okay. But then we have to add that back into the front one. So then we need 24 plus 2, which is 26. So then we're picking 24, 25, 26. This will be the address of the center element. Okay? So subtracting the front from the back gives us the number of bytes in the table. We divide that by 2 to get the middle byte of the table. And then we just knock off the low bit to make sure we don't get an odd byte. We don't want an odd byte at all. The number of bytes in the table has to be even. It's going to be even because each one of these is 2 bytes. It's an address of 2 bytes. I'm just checking. So if, for example, it started at 24 and went to 31, we still get the same thing. We get 31 minus 25 is 6. Then shift that right, divide by 2, which gives us the middle byte of the table. We remove that low bit, and we add that back into 25. And we're going to get then 27. So we have 25, 26, 27. That's good. See, I don't require that this table begin at an even address. That's not so important. All right, so let's get rid of this. So what we're going to have is keyword back minus is keyword front divided by 2. That is to say shifted right once. And then we're going to take that and we're going to remove the low bit, sort of functionally like this, okay? Do a logical AND with hexadecimal FFFE. I mean, we'll actually only AND the low byte, but whatever. We'll remove the low bit, and then we'll add that back to is keyword front. And that will give us the address of the middle element of the table. All right, and I'm going to hang on to this for just a few minutes to make sure that I don't forget it. Okay, here we've built is keyword front, is keyword back. Now we need to do that calculation. All right, and is keyword middle. Let's try that, okay? Yeah, I mean, I'm kind of thinking now that it maybe would have been easier to use an index instead of the addresses. Probably would have been. For one reason, the index would be only 1 byte long, and we would have 1 byte the arithmetic here would be 1 byte, not 2 bytes. And we're doing this addition anyway. So basically it's the same thing, right? Well, what we do here is keyword back minus is keyword front. We're just calculating how many bytes are in the table already. So if we already know how many bytes of the table, we don't have to worry about that. Right? The number of bytes in the table is keytoke minus keywords. Although it might be a good idea to put like an in keywords label here. So in keywords minus keywords is the number of bytes in the table. So I don't need to do this calculation here. Well, I mean, sorry, it is the same calculation, isn't it? That's just dumb. Okay. All right. I still think I'm going to leave this here because that's better than using keytoke, because now I can put stuff in here if I want to. I mean, I don't think I will, but it's available. So, right, so just change it to E keywords. Okay. All right, so set the carry, load is keyword back, subtract is keyword front, and I think I'm just done there, right? Technically, it's a 2-byte subtraction because these are 2-byte things, but I know for a fact that I have less than 128 pointers in here. There are 8. These are 4 in a line here. Here's 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 times 8 is 72, 73, plus another 12. There's 85 total pointers here. That's less than 128, and it's never going to be more than 128. So the number of bytes is always less than 256. So here I am, I should be done. Right? Because the worst that can happen is I get a borrow, and then when I go to the next, if I were to actually subtract the, if I just, let's just say, put that on the stack, then I get is, and I subtract is keyword front plus 1. This will be 0. It has to be, because the total size of the keyword table is not 256 bytes or greater. So there it is. That gives me the number of bytes in the table, which is this part right here. Okay? This part right here. And now I'm going to shift it down by 1, and then I'm going to divide by 2, and then I'm going to knock off the low bit, and then I'll add it to is keyword front. Okay? So shift it right. That divides by 2. And remove the low bit to make sure that we're talking about an even number offset. And now I can go ahead and add this back in to is keyword front. Whoops. Yeah, is keyword front. And this can be stored in 1 plus 1. And now just to make sure there's no carry, I have to add that into. Just add a 0 would be fine. Okay. So I take the number of bytes in the table by subtracting is keyword back address from is keyword front address. Subtract is keyword front from is keyword back. That gives me the number of bytes in the table. I divide by 2. I make sure it's an even number. I add that number of bytes to is keyword front to find the pointer in the middle of the table. I'm finding the middle entry of the table. I store that in stir comp 1 plus 1. And then I have to, what is this? That's supposed to be a 0. All right, maybe I'll just do it load 0 ADC. Okay, so that gives me, that's just in case there's a carry into the high byte. All right, and then I can store that in stir comp 1 plus 2. Okay. Now I think I'd rather have this part up here in front of this part, so I will do that. I'll just move that up there. Okay. So this is where I set up the, when I'm beginning, or the first time looking, I put that stuff, I get the, now this stuff up here won't change from loop to loop. It's the same old stuff. This part will change from loop to loop. So we're setting up here now the location of the element that we're going to test. So this is the text from the source file, and this is the element we're going to test here in strcomp1 plus 1 here. Okay, and now we can just call string compare. And what we're going to get back here is something either less, greater than, or equal to 0. If it is like not equal to 0, how to spell is keyword? Is that it? Yeah, is keyword. Okay. I'm just going to go down here. So if it's equal, this is what I'm saying here, it's equal. So this is the case where we found a keyword. All right. And what we need to do here is now get back out our pointer. This is the pointer to the element that matched right here. Maybe I want to do that first. Okay. And I want to subtract is keyword front from it. And again, this subtraction here is the high byte has to be 0. So I'm done with this subtraction. But this is the number of bytes that this pointer is offset from the beginning of the table. We actually just need the number of entries, not the number of bytes. So which entry number it is, so we can go ahead and shift that right, because the index into the table is the entry number it is half of the number of bytes it is of its location in the table by byte. So we'll shift that right, and then we can use this to index these other two tables here, the keytoke table and the keyval table. All right. Wrong place. All right. So we can load keytoke x. Be nice to do it correctly. And then we'll put that into the, actually, let's do the other one first. What's it called? Keyval? Keyval. It is keyval. All right, just do it like this. Okay, keyval. Store that into tokeval. Also, at this point, since when I come here, I have a 0 and A, I'm going to go ahead and store that 0 and tokeval plus 1. Because the high byte of the token value is going to be 0. Here's the low byte of the token value. And now I'll load the keytoke x, and we're going to return that. So we return this token here, this keytoke, one of these things here, as the token value. And then the scanning code, when it finds a name, it'll call this is keyword, And depending on what it gets back, if it gets back it's a name, then it'll say, okay, it's a name. If it gets back some one of these tokens here, it'll return that to the parser. So whatever comes back from is keyword is going to be returned to the parser, basically. All right. All right, so this is the success. Now, all we have to do is, if we made this comparison and the two strings were not equal, then we're here. And what we'll do first to say is, okay, well, if they're not equal, if our subtraction gave us, you know what, actually, one thing about that is that this thing returns that value in A that we got, right? But it's not, let's see, we branch if equal, this is where we compare them. Okay, branch if not equal to stir comp 2. So in this case, we're comparing two characters from the two strings, and if they're not the same, it will return here. And not only is this the subtraction, the value of the subtraction in A, but all the flags are set correctly, so we can use them directly. This is the case where we compare these things and we compared nulls, they were equal, and now we're comparing to see if it was a null, and it was, so we go down here. So it looks to me like in both of those cases we have good flags, right? If we go down here, then we're going to have either the flag set for this character was less than this character, or this character was greater than equal to this, greater than this character. They can't be equal because we branch only if not equal. In this case, we're comparing, they're both equal, the characters are equal, and we're comparing them to null. If they are null, then we go down here. So that looks good. Looks like that all of our flags are set well. We also have the way of coming down here. If we run off the end of the string, because the strings are 256 bytes long, in that case, we're going to have x goes to 0, and we're going to put that 0 in A, and we're going to have the Z flag set here. So yes, everything looks good. We can just use the flags directly. Okay, I'll call this is keyword 2. So this is the situation where the first string, this is the situation where the table string is greater than, that is alphabetically after the name. Okay, because we're comparing, this here is the name, and this here is the string from the table. So if the string from the table is alphabetically after the name, then we'll get back BCS. All right, so now we have the situation of the keyword tab entry is less than the name. And less means alphabetically before here. Okay, so if the keyword tab entry is alphabetically before the name, that means that we need to search the part of the table, since the table is in alphabetical order, after the current place, right? The current entry is alphabetically before the name or less than the name. So we need to search the stuff after that. So we have to adjust our is. What we're going to do is we're going to load remember, this is strcomp1 plus 1 and strcomp1 plus 2 is the pointer that we just checked. We're going to make that the new first pointer. Okay. And we're going to leave the back pointer the same. Although probably we should make it one more than this. In other words, we should go one past this one. Right? Because we just checked this one. This one is not equal to this name that we're searching for. So this should not be in the range that we're searching. We should actually move past this. There's two ways to do this. One way is just to go and add in a 2 while we're doing it. Well, okay, add 2, store it there. Store it there. Okay, so now we've taken the pointer to the entry or the address of the entry in the keyword table that we just checked, and we're adding 2 so that we're moving past it. In other words, if the one that we just checked was, for whatever reason, key W42, okay, so we're looking here. After adding 2, we're going to be looking here. This will be like last time, the first time through, this was the first one under consideration. And then the last one under consideration was this one here, because our back pointer points to the this space right after it. Now we found that means we were checking halfway through. So let's just say we were checking 42. That's the one we were checking. Okay, we found that doesn't work, and in fact, this is less than the value of the key of the word that we're checking to see if it's a keyword. This is less than the name that is alphabetically before the name. So we'll need to check the back half of the table now. So we'll make this the first, and we'll leave the last where it was over here. And we'll check this range. On the other hand, if this was alphabetically after the name, we're going to check this range here. And we're going to do that by making this the back pointer. And in both cases, this will be excluded from further consideration because obviously it didn't match. Okay, so we're altering the front pointer so that we're now searching the back of the table. And once we've done that, we need to go up here. Okay, if you don't remember, A and OP just means do nothing. It's just a way for this assembler, you have to have this if you have a label all by itself in a line. Yeah, put a blank line there. Okay, because this is where we calculate which is our middle pointer, right here. So we've just adjusted the front pointer, and then we just jump up here to check the middle pointer. I mean, to make a new middle pointer for this new part of the table that we're looking at. Is keyword 1. Or let's make it 0. Okay? And here's the part where we have to check where the element of the keyword table that we just checked is alphabetically after our name that we're checking. So here we just need to move the thing that we just checked and make it the back pointer. And here we don't need to add anything, because if you remember, the back pointer is pointing after the end of the table or after the end of the part we're checking. So we just do this and we jump back to is keyword 0. All right, and here's we got a match, right? We match the name of the table. All right, the only thing we have left to do for our binary search here is the end condition, because it's not going to ever end. So what we need to do is we need to check to make sure that this thing ends sometimes. And the way that we can do that is right here when we're subtracting these two. Okay, if these two like we have the situation, like imagine that we've checked the whole thing. We're cutting in half the area of the table we're checking each time we check. We have a situation where we're checking this pointer here. So is keyword front is pointing here, and is keyword back is pointing directly after this pointer. So there's only one pointer in the range that we're checking. All right, and if this thing is, this pointer here is less, alphabetically less than the name, we're going to basically move this thing here on top of that. So it will then be equal to we'll move it to the next thing, will be after here. And if it's less, then we'll move. So like if this, you see right here, if the entry is alphabetically less than the name, then what we'll do is we'll set is keyword front to be the address of this thing plus 2, which will be the same. It'll move it here. If this is greater, that what we're going to do is we're going to set this to be is keyword back. So that means we'll move is keyword back right here. And in any case, is keyword front and is keyword back will be the same thing. I mean, this illustration is bad and maybe I explained it wrong. So let me just imagine we have an address ABCD, and at the address we have our pointer. And is keyword F has the value ABCD. That is to say, it's pointing right here. This one has that plus 2, AB, CF. ABCF. That's that plus 2, DEF. Okay, good. All right, if the string that points at this is alphabetically less than the string of the name we're checking, what we'll do is we'll take this thing here and add 2 to it and store an is KWF. So notice it'll be that. So these are now the same. If this is alphabetically greater than the string we're trying to check for, the name, then what we'll do is we'll take this and put it in is KWB, like that. in either case, these two now will be equal. That's the key. So when we do this subtraction here, if the result is 0, okay, and that's even before we shift it and all that stuff. If the result is 0 right here, that means we've searched the whole table and we didn't find it. Okay, we searched the whole table, we didn't find it. So what I'll do here is I'll just say branch if not equal to 0 to is keyword 1. And that's right here. Okay, so if what we get here is not 0, then we say we're not done yet. We're going to keep looking through. If it is 0, then we're done. So this is the done situation. Okay, didn't find a name in the table is here. And what we're going to do is go ahead and load that tnam token and return it. So if we don't find the name in the table, okay, now this is the loop. Find a search in table loop. Okay, I'll just get rid of that ANOP. This is the binary search in table loop. And if we don't find the name of the table, then we just return tname. So it's the token. What kind of token is it? It's a name. If we do find the search in the table, this is where we search the table, then we're going to return whatever's in the key token table, which is one of these things here. Okay, so what I'll do right now is just check for assembly errors. I see that's, yeah. That was just my dumb little thing. Let me get rid of that right here. Okay, got an error. Okay, Tocqueville. So let's look for that. Tocqueville. Oh, I see. That is because Tocqueville here is not globally available. Here it is. You know what I think I'll do? Rather than try to make this available to the other file, I'm just going to return the toc value in X, and then it can be put in there. All right, so here I'm not going to put this into Tocqueville. And that means I don't have to worry about this. Here I'm just putting a 0 in there. I don't have to worry about that. I'm actually going to just, oh wait, I can't move into X because I'm using X, so I just move into Y. Okay. So what I'll say here is, just a little note at the beginning. Okay. returns token in A, returns tokefile in Y if token is not name. Okay, save. Just to make sure there are no other errors in there. And there are not. Okay. So now I need to go here to the scanner. Here we go. And right here is where I check for name. Okay, and I jump to get name. So here's the get name subroutine. All right, and what it does is it right now is it ungets the last character, which is not a named character. It loads A with the 0, and it's putting a 0 into the basically it's just null terminating the thing, and then it loads. It says okay, it's a name and returns, but actually we don't want to do that. Now we're going to call is Kiwa. That's in the other thing we just worked on. And now we're going to check. When it comes back, it's going to have the actual token in A. We're going to compare that against tnam. If it's not, then we'll have to go to get name. Let's just say 8. Yeah, get name 8 is available, no problem. Which is just the RTS. Okay. If the token that comes back is not name, then what we're going to do is go ahead and store the Y value in tokefile. And while I have this A here, I'll just store that in tokefile and in tokefile +1. Just clear out tokefile completely. So I'll store that Y in tokefile and then return whatever token is keyword brought back. And actually, I don't need. Yeah, I guess I need to do this branch as long as I'm not sure that Y is 0. I think what I'll do is I won't do this branch. I'll just go ahead and JSR is keyword W. In fact, I can jump is key W. Right? I'll jump to is keyword and let it return everything correctly. No, that doesn't work because, yeah, there's no way to change tokefile there. Oh, okay. What I'll do is there's JSR here. JSR is keyword, and then I will store Y in tokefile no matter what. I'll store that there, and then return. So I'm storing the whatever's in Y from is Kiwa, store that in tokefile, and then return with my token in A. And just go back here real quick. Is Kiwa, and search for that. Here it is. And I just need to make sure that Y has some reasonable thing in it, no matter what happens. Right? So here, for example, I should probably say load Y with 0. And down here, I'm getting a y out of the key val table, so that's all good. So now y will either have a real token value to put in the toke file, which is basically an opcode, or we'll have 0, and everything should be happy. All right. The last little thing we have here, so like assuming that that code works, which it may very well not, but assuming it works, then what happens is if we call our test program here, our little test code right here, print token, that if it gets something like it doesn't know what the token is. So here it's going through comparing the token it gets back. Okay. It moves the token into X here. And then, yeah, is it a right shift? Is it a left equal? Blah, 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 blah. If it's a name, it goes here. If it's EOF. So basically what it's saying, if it's none of those things, it assumes it's just a character and it prints it. Okay? I think what I ought to do instead is have here a PR token. I'd like to do something better, but for the time being, I'm going to say compare X to, and remember that the single character tokens are all less than 128. Okay, and if it's less than 28, go to PR token 11. Otherwise, that means it's some special token which I didn't account for up here, which is greater than 128. That is one of the tokens I just created. And I can print it out as a hexadecimal. And so print out the hexadecimal, then just go down here to finish it off. So that is a little all right, and let me assemble it to the printer. Everything looks good. This episode's already gone on quite long, so this is going to be the moment of truth. If it doesn't work, which honestly I would be kind of surprised if it did work on the first attempt. But if it doesn't work, I'll come back next time and figure out what's going on. If it does work, then we'll say hooray. But in either case, this will be the end of this episode because it's probably already an hour and a half long at least. All right, let's say test. And we'll send that to the printer again. Okay. So it didn't quite work. We can see that everywhere I have any kind of name, it returns DB. DB here. And that's not right. DB. It's in here. Yeah, it's not even one of my things. So I'll have to figure out what's going on there. But we'll do that next time. So until then.